Problem number 2 states, the veil of a wedding dress is held up by balloons as shown below. If the mass of the wedding veil and balloons is 0.4 kilograms, what must the total volume of the balloons be? They want us to assume that they're full of pure helium with a density of 0.166 kilograms per meters cubed, and they've given us the density of air as 1.20 kilograms per meters cubed. Okay, so gone ahead and drawn out my little version of their picture here with the balloons holding up the veil and written out our variables given. So we have the mass of the balloons plus the veil equal to 0.4 kilograms. We have the density of helium. We have the density of the fluid, which is the air. So I've labeled the density of air as the density of the fluid. And then they want us to find out the volume of the helium. So we can draw this as a force diagram here, and we can label our forces acting as so the object here is our veil plus balloons helium. That's all just the object that I've drawn here. So we have the buoyant force, so the force of the fluid acting on the object, which is the force of the air pushing up on it, equal to, because we're floating here, we're just staying still. So the buoyant force is equal to the weight of the object. So the mass of the object times gravity. And because we are in a state of neutral buoyancy, we know that the average density is equal to the density of the fluid. And we have to note that it's the average density here because we're working with a compound object. If it was just a uniform object, like just a block of steel, let's say, in a water tank, and it was floating, we would know that the densities were equal to each other, and then we could just take, the mass and the density and find the volume, and then find the volume just using that. But since we have the mass of both, we need to take into account that we're going to have two different densities. So this average density is equal to the density of the fluid, which, like I said, average density is the mass of everything, every part of the object divided by the volume of the object. And because we are fully submerged, we know that the volume of the object is equal to the volume of the fluid. So you can note that here for later. We can just set those two equal to each other. Okay, so we know that the buoyant force, the magnitude of the buoyant force, is equal to the density of the fluid times the volume of the fluid times gravity. We know that the weight of an object is equal to its density times its volume times gravity, or the mass times gravity, because mass is density times volume. And we can use both of these for our equation because, like I said, we need to take both weights into account, the weight of the balloons and the weight of everything else. So we can set our buoyant force equal to the weight of the helium, or the weight of the balloons, plus the mass of all the other stuff times the gravity. And we can just do a little bit of algebra here. I subtracted the weight of the object, set it equal to mass times gravity. We can factor out the densities here. So, like I said earlier, the velocity or the volumes are equal to each other, so we can just factor out an overall volume times gravity, which gravity is also factored out, or not factored out, but canceled out. And then we're left with our volume equal to that mass of the veil plus balloons divided by just the density of the fluid minus the density of the helium or the balloons, which is what we're solving for. Or no, sorry, which is what we're given. Cut that out right there. All right, yeah, volume is equal to mass over density minus density. So yeah, we can plug all those in because we were given all those variables, and we are left with the volume equal to 0.387 meters cubed. And this all relates to what we're learning in chapter 4, or 14.2 specifically, on buoyancy and Archimedes' principle, which is that a fluid exerts an upward buoyant force on an object immersed in or floating on the fluid, and the magnitude of the buoyant force is equal to the weight of the fluid displaced by the object.